Look at the water line in this glass. The straw appears physically severed, completely offset from the top half. The standard high school physics explanation for this is refraction. Light travels at roughly 300 million meters per second in a vacuum, but it slows down when it hits a denser medium like water. That sudden drop in speed causes the beam of light to bend. To visualize this, teachers usually use the car and the mud analogy. Imagine an off-road vehicle veering off a paved road and hitting a muddy patch at an angle. The right tire hits the thick mud first and slows down. The left tire is still on the pavement, moving at full speed. That difference in drag pulls the car inward, forcing it to pivot. That makes intuitive sense for a large physical object. But light is made of photons. Photons are point particles. They don't have a left or right side, and they certainly don't have tires to experience physical drag. There is no physical mechanism for a single photon to pivot out a boundary. Since a photon can't drive like a car, classical physics offers a different rule, Fermat's principle of least time. This states that light will always travel between 2 points by taking the path that requires the absolute shortest amount of time. Think about it like a rescue mission. Suppose your camera drone loses power and crashes into a lake. You're on the shore and you need to get to it as fast as possible. Your gut instinct might be to run in a perfectly straight line directly toward it, but this map shows the actual fastest route. You run much faster on land than you swim in water. To minimize your time in the slow medium, you should run further down the shore, past the straight line point, and then cut sharply into the water. The total distance is longer, but the travel time is shorter. This optimal, bent geometry translates perfectly to optics. Light minimizes its time in the thicker, slower water by bending its trajectory before reaching your eye. But this leaves us with a massive logical hole. Light doesn't have a brain. It can't survey the landscape, calculate trillions of potential routes, and select the single fastest option before it even starts moving. So how does a mindless particle know exactly where to go? It doesn't. To answer this, we have to throw out classical physics entirely and use quantum mechanics. In the quantum realm, a photon doesn't pick a single route. Until measured, it exists in a state of superposition, taking every possible path at the exact same time. To make sense of this, physicist Richard Feynman developed a mathematical framework that calculates how all those simultaneous paths interact. We visualize his math using phasors, tiny, rapidly spinning clock hands on every photon path. As the photon travels, the arrow spins fast. Upon arrival, it stops. Different path lengths mean each arrow locks into a specific direction, based purely on exact travel time. Feynman's rule for finding the true path is remarkably straightforward. We just take the final, frozen clock hands from every possible route in the universe, and we add them all together. Look at extreme paths bouncing off the ceiling or looping chaotically. Their wildly varying travel times mean their clock hands arrive pointing in completely randomized directions. Added together, opposite vectors cancel out, destroying the probability that the photon takes those chaotic routes. Now look at the tight cluster of paths surrounding the mathematically fastest route. Because they're almost perfectly identical in length, their spinning clock hands stop at nearly the exact same angle. These aligned arrows reinforce one another, mathematically stacking up to amplify the probability. The straight beam we observe is the surviving average of this quantum chaos. All the inefficient, wrong paths have successfully destroyed each other, leaving only the most probable route behind. That quantum averaging dictates exactly where the photon emerges from the water. But there's one final step in the journey. That surviving photon eventually strikes a photoreceptor in your eye. Your brain processes that hit, but it makes a biological assumption. The human visual system automatically traces incoming light rays straight backward, completely ignoring the fact that the light just bent at the water's surface. The reason for that blind spot is written into our evolutionary history. Our hominid ancestors evolved in terrestrial environments, where light generally travels through the air in a straight line. Spotting a predator on the savanna requires rapid visual processing, not precision underwater optics. There was zero survival advantage to developing a brain that continuously calculates complex refractive indices in real time. The sight of a broken straw reveals the point where the mechanics of quantum superposition meet the survival instincts of human evolution.